A rooftop sample in the Stanford experiment became colder than the air around it, while direct sunlight was still hitting it. No compresor. No fan. So how can a surface lose heat while the sun is trying to add it? Every warm object emits infrared light. Most of that radiation is absorbed by the atmosphere, but there's a useful gap between about 8 and 13 micrometers. Through that window, some of the surface's heat can radiate upward toward the cold sky and space. The catch is that an ordinary black emitter also absorbs sunlight. The researchers built a photonic surface from 7 alternating layers of hafnium oxide and silicon dioxide. It reflects 97% of incoming sunlight, while emitting strongly in that infrared window. Shortwave heat is rejected. Long-wave heat gets an escape route. They put that surface on a low-conductivity pedestal and added an infrared transparent windshield. This is a reconstruction of the rooftop apparatus, not documentary footage. The point was to stop warm air and warm supports from quietly feeding heat back into the sample. Under direct sunlight above 850 watts per square meter, the sample cooled to 4.9 degrees Celsius below the ambient air. At ambient temperature, the measured cooling power was 40.1 watts per square meter. The result came from the published rooftop experiment, not from the illustration on screen. This is passive radiative cooling. A surface can reject heat without an electricity input. In practice, a roof, water loop, or solar panel could use a similar surface to dump heat, but clouds, humidity, wind, sky view, and heat leaks all matter. 4.9 degrees is a measured prototype result, not a promise that a coating replaces air conditioning everywhere. The trick is not finding a magically cold material. It is choosing which wavelengths the surface reflects and which it emits. When someone claims a passive cooler, ask 3 questions. What sunlight does it reject? What thermal radiation does it emit? And how is unwanted heat kept from leaking back in?